Okay, so welcome everybody to this seminar at the Department of Mathematical Sciences at Chalmers University of Technology and University of Gothenburg. My name is Umberto Picchini, and today our speaker is Professor Serik Sagitov. He's a professor here in mathematical statistics, and he's also the head of the division of applied mathematics and statistics. His talk is, of course, related to his major interest in this critical branching is a pure depth process coming down from infinity. And as you see, we are trying hard to give seminars in the hybrid way. It's always a pleasure that we have a speaker, and today we have a local speaker. So thanks so much, Serik, for accepting to give this talk. And feel free to start. And if someone wants to ask questions during the talk, well, feel free either to unmute and just ask directly. And if you don't feel like, you can write in the chat, of course. Please, Serik.
Thank you, Umberto. The title of my talk is the title of this preprint available on archive. And the idea was that it should sound a little bit controversial. It says about branching phenomenon. And on the other hand, it's a result where it can be considered as a pure death process. So branching means that you have individuals that give birth. So you can think of a typical trajectory as a branching tree. And the pure death, so there are births and deaths. And the pure death process is just only deaths. So you have the number of individuals which only goes down. So I will try to explain what does this really mean. And this picture, it's something I calculated from the limit process. I've got a question from somebody who got an announcement about the seminar from Umberto, and I hope it's a person from Egypt. So I hope this person is now with us via Zoom, and I will try to answer to all the questions that arise. So one of the key words here is Vatutin's dichotomy, and I will explain everything step by step. I will start with this preamble, which illustrates also the idea, illustrates the branching phenomenon as a very universal one and fundamental. It appears in many situations. In particular, if you think of the how the research develops, where there are academic fathers and daughters, and then my academic grandfather is Boris Alexandrovich Sevastianov, who is actually the, you call it, honorable doctor at Chalmers. And right. So he's a descendant of Kolmogorov. So I'm very proud to consider myself a direct descendant of Kolmogorov in the academic sense, but also genetically, I consider myself as direct descendant of Genghis Khan. And there are other useful things to think about when it comes to branching. For example, coronavirus, how it spreads. It's also a branching phenomenon, and we consider, and every progress in studying this branching process model is of course welcome, because it's so fundamental. So this citation of Sevastianov is not 100% perhaps exact, but he said that Kolmogorov was the father of probability theory. He used the excavator, and then his children, academic children, used big spades. And the next generation used scoops and then spoons and the toothpicks. And what I'm going to show, what I have achieved using my toothpick in this direction. And to explain this, I would like to show you the map which leads to this phenomenon, which was found by Vladimir Alexeyevich Vatutin. He is my academic father. He is not much older than me. So in 1979, in the Russian original paper, he produced the result, which is depicted here. I call it, perhaps the first one, call it Vatutin's dichotomy. And you see that there are many steps, many details before you come to the right phenomena to study. So it's very important that if you use the toothpick, then you pick at the right place. And I think I worked in exactly the right place to work on, and I will explain what I've done. So when I put this slide on the Facebook, then Peter Jager commented, there is much more on this graph. So what I just shown some, for example, Torgny Lindwall produced many interesting results outside this. For example, in the case of varying environment where the reproduction law is changing all the time, there is a famous result by Torgny saying that there is a limit theorem of almost sure convergence, which is very non-trivial in the branching science, in the branching framework. Okay, so let me show you some. I start describing the main object of my study, critical branching process, by referring to these historical papers, which starts from the simplest model, branching process model. It's called Galton-Watson process, where, and all the time I focus on critical branching. Critical branching means that every mother has exactly one daughter on average. This is the critical regime of reproduction, where the population is in harmony with the environment. Otherwise, you can get the supercritical or subcritical reproduction laws. So Galton-Watson means that every individual lives exactly 1 unit of time and then produces a random number of offspring. Okay, so everything is described in terms of one random variable, n. It's the random number of offspring, and criticality means that on average, there is 1 offspring on average. Okay, but then the next model, Bellman-Harris model, and Vatutin has worked with this model, Bellman-Harris model. It says that the life length L is not deterministic, it's a random. So you have capital L units of time, and then in the end, you again produce a random number of offspring. So now the model, yes.
So 1 offspring, does it really mean? So 1 offspring.
Okay. So 1 offspring, does it really mean 0 offspring in the sense that the mother continues to live on, or is?
Well, it's you think correctly. So one can treat this as you have first you have 1 mother with 1 offspring,
Yeah,
and then with 1 offspring, and so on. But this will not satisfy the assumption of independence. Our assumption is all individuals live independently according to the same reproduction law. And the reproduction law in the Bellman-Harris case says that you live a random time, then you reproduce, give a random number of offspring, and they too are independent.
yeah. But I'm wondering, because in the Galton-Watson, then if you would have one offspring and the parent continues to live, then you would have a growing population. Yeah. Yeah. Okay, and then you die. Okay.
Yeah,
okay. Thanks. Okay. So
exactly. Yeah.
Okay. Yeah.
Yeah. So this
Okay.
is
So then I get.
Yeah.
Okay. Thanks.
Death, it splits.
Okay.
Okay. In this sense, maybe it's biologically, it's not very realistic, but if you think of coronavirus, then it's exactly the case.
No, it's fine. I just wanted to.
Okay, very good point. Then the natural question is how we, so there are here we have what? We have overlapping generations, and then we have to define, measure the generation size. And the generation size is measured, in the critical case, is measured as the expected life length. Okay, the expected life length A is a very important feature of this age-dependent model. So 1964, Sevastianov introduces a more general model where, again, it's reproduction by splitting in the end. But now we allow for dependence. And of course, it's much more complicated mathematical model. What is the average life generation size? Now it's the expectation of the product, the life length multiplied by the number of offspring. So it's a not very trivial observation, but it's also important that we are talking about the critical case. Then 1969, two groups of people, Kramp-Moth and Jager, our own Peter Jager, introduced a more general reproduction model where now the trajectory of the reproduction law of a single individual looks like follow. You are not supposed to produce only in the end. Now what you're saying, you can have offspring at different ages. And it's much more complicated because you can think of all possible dependencies. If you produce the offspring young, then perhaps you have less opportunities to produce it later, and so on. If you live longer, then you can produce maybe less on average, and so on. So this is very complicated mathematical object. And if when it comes to the average generation size A, then the formula is this one. So it says that if all birth times, if births are produced in the end of the life, then all of them are equal to L, and we are back from here to here. Okay, so there is a clear connection with the previous model. I'm not, so this, but this is of course not a trivial result, and I'm not sure myself. I think as it was the invention of the founding of Peter Jager, but maybe there are other biologists who produced it in a different way. Okay, so these processes usually called Kramp-Moth-Jager, but to stress this discrete time feature, I call them Galton-Watson process with overlapping generations. So this O will stand for the overlapping generation. Okay. So I start with the Galton-Watson process to make clear what my statement is. So what is a Galton-Watson process? The model it's a Markov process on this simple state space, 0, 1, 2, and so on. We start from a single ancestor, like Genghis Khan, and count the number, in this case, of male descendants. And everything is described by a single variable, the number of offspring. In this case, in this sense, this model is as fundamental as the random walk. where you also have only one random variable, is the jump, which can be positive or negative. And if you think of the symmetric random walk, then it will somehow correspond to the critical case, because you produce one on average, so you stay more or less on the same level. And the way to study this process is through this branching property, which says this is the original process and these are the daughter processes. You have a random number of copies after one unit of time, and you have this equality in distribution. You compute the generating functions, you find a recursion, and then you work with this. This is the toothpick, the simple tool to analyze. But the analysis can be quite delicate to produce the interesting result. So my focus here is in the case of finite variance. So here comes the first important parameter, B. B describes the variance of the offspring number. It's not zero, otherwise it's trivial model, but it is finite. So for this critical Galton-Watson process, we know that the process will always be absorbed at zero. You cannot stay forever positive because it's absorbed at zero, the process. And for the survival probability, there is a very elegant formula saying that as t grows, then it's inverse to the time. So if you observe the process after 1,000 generations, the probability of the process of survive is very small. It's the inverse of the number of observational time. And it's very important to recognize the role of the variance. The larger is the variance, the faster this critical process extincts. Okay. So mathematically, it's a very nice, a simple but very nice example where the expected value is always 1. Whatever is t, it's on average, you expect the population size to be 1, but we know it will extinct with probability 1. And this is accompanied with the feature that the variance grows linearly. Okay, very nice example of this, of such a distribution. And as a result, we get this claim, which very important in the current content, what I'm going to show you for the Galton-Watson process with overlapping generation. And for me, it's important that you understand what is the claim here. So what is t? T is the time of observation, which is remote. So we assume that we observe the critical process to survive after, let's say, time 1,000. The probability is very small, and you would say, well, it's why would you concern about this? If you think of a large population of coronaviruses, who are like million, and assume that now it's in a balance with the humans, and each virus produces one new virus on average, what happens after 1,000 units of times, or 1 million in this case? Most of them will die out, but a Poisson number of them will survive. And then it's interesting to see how does it, what is the population size of the survival ancestors? Okay, so t goes to infinity, and this says we trace the population size in this new scale. So y is the rescale time. Okay, so y equals 1/2 means it's half of the time before the time of observation. 2 means that after 2 million units of time. Okay. And it says that there is a convergence of finite dimensional distributions to a limit And the limit is very strange. It's either infinity or zero. What are these numbers? This is the number of individuals in the population. So it can be 0, 1, 2, 3, 4, 5. There is no normalization here. So I do not divide by t, for example, which is the usual normalization for the critical process. It's just the without any normalization, and the limit is infinity or zero. Another important thing that we do not include zero. Okay, so this gives the following picture. If I start with one individual, the critical process, here is remote time t. Yeah. So I will, yeah, just for a while. So what happens? How it will survive this critical process? It turns out to survive, it should quickly grow. It grows to the level of t, but very quickly. And then it stays on this level. And then after a while it dies. This is the survival strategy of the critical process. So what does this say? In the limit, you can think the limit processes, if we exclude zero, it goes, the limit process goes as follows. We are sitting at infinity, okay? We are sitting at infinity for a random time t0, and t0 times t, because t is the scale. And then at this time, it goes to zero. So it's very many individuals in the population, and then instantaneously dies. This is how it behaves, okay? So if you do not understand this picture, then I'm in a big trouble, because this is the simplest you can go. Please ask your questions. I hear you from the Zoom.
Is there any significance to the fact that T0 has infinite mean in this picture?
Not really. It's just a random variable with this density.
Okay.
It's just a matter of calculation. But it's a good observation, yes. And it comes to this, it's because of these peculiar properties of this model, where you have the mean is 1, and then, so perhaps you didn't hear the question. The question was, is there any relevance that the expected value of this random time is infinity? This is the density, okay?
Serik, one more question about that. Is the parameter -2 actually relates to the fact that the variance is finite? So for instance, if the variance is infinite and say has a moment 1.5, would that then be y minus 1.5? So, and you would have something like heavy-tailed, maybe stable distributions.
So Sergei's question in the Zoom, this -2, does this relate to the finite variance? And the answer is yes. So the infinite variance case will give us a new parameter alpha, which describes the tail of the distribution of the number of offspring, and it will appear in the answer.
Mm-hmm.
Okay.
Okay.
So, but I don't want to focus on this for too long. My wish is that you understand this picture, that in the limit what we get is a pure death process coming down from infinity. For the Galton-Watson process, it's a trivial one. You are at infinity and then go to zero. What we are going now to study is the case of age-dependent process, where you have long-living individuals. And to prepare for the final result, I would like to say something about the Bellman-Harris case. And the Bellman-Harris case is described by this more complicated branching property, which says that the daughter processes appear at random time L, and the original processes, this is 1 if the original have survived, plus the number of, plus the contribution of daughter processes at time t. We assume again that the variance of the critical case variance is finite, positive, but we also need some condition controlling the life length. And the life length condition boils down to this one, which says that we need some parameter there, which would be properly to call Vatutin's parameter, which controls the tail of the life length distribution. If D is positive, it would mean that there are a finite number of long-living individuals in the process. Long-living means if our observation time is 1000, then the individuals live 500 units of time. So the life length is comparable with the scale of our picture. Okay. If D equals 0, then we more or less in the Galton-Watson situation, where there are no long-living individuals. So if D is finite, then in the Bellman-Harris case, of course, it will imply that the generation size is finite because it's the expected life length. And the Vatutin's result, one of the results says that the asymptotics of the survival probability has the same form as for the Galton-Watson, but it's more complicated factor here. It includes not only B, but also A and D. A is the expected life length. D is this Vatutin's parameter. So if D equals 0, then we are essentially back to the Galton-Watson case. And from here, I go to the general case of Galton-Watson process with overlapping generations. Much more complicated branching property. And as a particular case, we get the Sevastianov process. And for the Sevastianov process, it is good at least to illustrate this more complicated case where you have different ages and there are any possible dependencies. So if you look at the Sevastianov process, the expected generation size is the expectation of the product, and you can express it as the covariance between life length and the offspring number, plus the expected life length. So what we see, if they're positively correlated, the life length and the offspring number, then your generation size on average can be larger than the life length. So it's a bit counterintuitive. Okay. And there is, even in the Bellman-Harris case, this condition came automatically. But in the general case, even if the life length has finite average, this parameter A can be infinite. And this is illustrated by this counterexample. It's a very delicate, although case. So we see that we need a double logarithm to describe the tail of the life length. So I leave it and go further. So it says main result. Now I can formulate the main result, which says, which is remarkable in that sense that the model is very complicated and there are lots of dependencies. And all of a sudden, the result, this is the same kind of result I showed you before. I just follow the number of individuals in the population. It converges to a pure death process coming from infinity. And the limit process is described in terms of a single parameter C, which is a compound parameter involving those three that I introduced before. It's a very remarkable result in that sense, very complicated model. And the limit is described by a single parameter, C, despite all possible dependencies. So you don't need covariances and so on. And the description of the limit process, I will give some formulas a little bit later. But the description is compared to the Galton-Watson description that I had before, is the following. Now, instead of a single time where you go down from infinity, you have two times. You have a time capital T where you go down from infinity. But then you do not go directly to zero. You can end up like with three individuals, then 3, 2, and then at some point T0. So this is T coming down from infinity, and at some random time T0 you go extinct. So the difference with the Galton-Watson, that now you have a few long-living individuals which will give your population, keep your population alive. If I would connect to our own department, we have a number of long-living individuals. Two of them are sitting here. We have also Olga. So this is also an illustration of the process with overlapping generations. Okay. So we have two random times. This is an important issue here. Capital T coming down from infinity. And capital T0 is the extinction time when it goes this pure death process. And at this point, I would expect why the branching process is approximated by pure death process. Because this, even if these are long-living individuals, they give birth to children. And the answer is because of the time scale. The time scale is very long. You can produce offspring, but they disappear undetected. Okay? This is the reason it's finite dimensional distribution. This is the form of the convergence. You cannot do this Korohot type convergence, because you cannot detect them at any particular time. You cannot detect the children to the long-living individuals, even though they exist. But how you catch it, you should be kind of a guess very correctly. Okay. So now
Serik,
I can, yes?
Can I ask another question?
Yes.
You said you come down to zero in just a finite number of steps, even though it's from infinity in the scaled limit? It doesn't take sort of an infinite number?
So the question of Jeff was, is that it's just a finite number of steps to come down to zero? And my claim is that from infinity, by one giant step, you come to a finite state. This is the concept of coming down from infinity. It was observed also for the coalescent process. Not all pure death processes have this property, but this, in this case, we go down from infinity by just a single step. Of course, if you zoom in, you will see many, many small steps, but because the scaling is this large, then for us, it's just one single step going down, okay? And what Vatutin's dichotomy says, that the critical branching processes, age-dependent, it can survive for two reasons, either many short-living individuals or a small number of long-living individuals. And this result that I produce, it gives another perspective. You can think of a wave, infinite wave of individuals, but then it drops down. And the question is, will it drop down from infinity before or after the time of observation? If you drop down after the time of observation, you survive because of the large number of individuals. If you drop from infinity before, then it's due to the small number of long-living individuals. So, to give some formulas involving this constant C, you remember that everything in the limit process described just by a single constant C, which involves B, D, and A. So here it appears this constant C. And once again, there are two important random times. Capital T is the time of coming down from infinity, and T0 is the absorption at 0 time. And if constant C equals to 0, it means that there are no long-living individuals. T equals to T0, and we are back to this picture that I shown you before for the Galton-Watson process. You stay at infinity for a while, then you drop to 0 by one jump. But if D is between 0 and infinity, it means that C is positive also, this constant C. Then you can actually compute the density function for the time T by this formula. And the answer depends on whether you are before the observation time, which is represented by 1, or after. And interestingly, here you see how you have two different. So this black solid line, it's as before, as Jeff said, this infinite with infinite expected time. This is the T0, okay? It's the same all the time. But T, the time coming down from infinity, it will be different for different C. And we see that the density has a jump at 1.
Can you remind us what was the definition of C and D? Because they now have
yes.
crucial role.
I agree. So what is D? D is the Vatutin's parameter describing the long-living individuals.
Okay.
So if D is positive and finite, it means there will be a finite, a compound Poisson number of long-living individuals. And B is the variance of the offspring number. A is the average generation size. So then what would be this C? C is this one. This is the variance, this is Vatutin's parameter, and this is your parameter.
What is the expected?
This is the average generation size. Okay. So it's a bit difficult to find an explicit intuition, direct intuition of this parameter. But the important thing, one single parameter describes the limit behavior in a nice way. And of course, it's very important that we have this limitation, finite variance, finite generation size. Then all of a sudden, all these dependencies are in control. You exclude some unpleasant or difficult scenarios. Okay. And you see that how it changes with parameter C increasing. The extreme case, two extreme cases, C equals 0, then this will too coincide. And C equals infinity, it means that the role of long-living individuals is much stronger. It's heavier tail for the life length, and it will be a different behavior, which I do not discuss here. So there are more formulas which I skip, and I would like to say something about the proof. As I mentioned, this is the toothpick it's very elementary in that you start with this stochastic recursion, and you translate into the recursive equation for the generating function. But what remains to do is very delicate analysis to produce the result, where you get, in the limit, you get a quadratic equation. So if I would go to the school and explain why do you need quadratic equations, I can perhaps refer to this result. But as I said, the analysis is very complicated. Even in the Bellman-Harris case, Vatutin, it was quite an achievement of Vatutin to obtain this result. And if we can go even back to Sebastianov, who used a very intricate tool to analyze these equations that appear in the limit. And I wanted to share with you my experience with this proof, where I changed it so many times, trying to kind of finish it, and failed many times and try it again. And at some point I had this existential experience. Why I'm doing this? Why I listen? Why I do it? Instead of sleeping, I do this. Because in the end, nobody is going to read the proof in full details, maybe one person. My hope is that in 100 years, somebody will go, some student will go and read it. Of course, I exaggerate, but very few people will read all and check all the steps. But my feeling was that this is it's very important and should be recorded. And this is my duty. I have to do it. And I feel like I succeeded. And I would like to finish with this announcement that we are in January. We will announce a position of a PhD position at our division. So it's free in that sense that the top candidate will choose the project or the supervisor at her or his will. In the announcement, there will be, just to illustrate, there will be some project mentioned. My own project proposal is called Critical Galton-Watson Process with Overlapping Generations. And the aim of this project is to investigate the cases where these finite variance and finite generation size are weakened conditions. And then you can think that there are many possibilities, like you have a long living individual which produces lots of children, and then there will be new and interesting phenomena. I can mention Topchi, Valentin Topchi from Novosibirsk. He's a clever guy who produced many results published in obscure Russian manuscripts, and nobody read his results except me, who tried to understand all the details. I could not follow all the details of his proof, and of course these results should be worked further on, and doing it like baby steps, like I considered fully this simple situation. And there are also new limit theorems to be discovered for this interesting model. Thank you for your attention.
Thank you very much, Serik. So now it's time for questions. And I would like to say first, if you here in the audience, you have a question, let me know, raise your hand and I'll pass you the microphone. And do we have also any question from Zoom?
I have a question, yes.
Yeah, Sergey, so just a moment. So yeah, unfortunately, we don't have a speaker here. So Serik, you're probably the most well equipped to understand each question. So
I will repeat your question.
Okay, Sergey, go ahead.
Serik, I remember there was a notion of Yaglom distribution, which is exactly the distribution of the process given that it has survived to infinity. Is there any relation to your, say, process ETA?
Yes, Sergey asks about Yaglom theorem, which also gives the discrete distribution in the limit condition on survival. This result is for the subcritical process, and it's of course very related to this phenomenon. But this is not due to the long-living individuals. It just, if you survive for the subcritical, then it's the strategy in the subcritical case is just to keep some number in the population. It will not go to infinity, but it always will be discrete. And it will actually be some kind of a branching process with immigration. It means one individual will always produce positive number of offspring. Okay, you can imagine this one. So it's a different picture, but the result is closely related. Namely, we condition on survival and we observe a finite number of individuals in the population.
Thank you.
Any further question on Zoom?
Yeah, I had another question. Serik, in the second scenario, not where it goes from infinity down to zero, but where you get this death process, is this death process a regular death process in the sense that it's Markov, but perhaps it's not time homogeneous?
So Jeff's question is, if we look at this part, suppose we went down from infinity, how this process behaves? Is it a pure death process having Markov property, and if it is, then is it time homogeneous? The answer is that it should be further, of course, investigated, the details of the limit process, but it should not be a Markov process, because how these long-living individuals appear? You have lots of individuals here, and each individual, it's like a Bernoulli trial, which may or may not produce a long-living individual. So the appropriate picture would be that there is a wave of many individuals, and some long-living individuals were born, okay, at some random times, okay, and then when the wave disrupts, what you see are those long-living that continue living by inertia. They will produce perhaps offspring, but very little offspring, very few, that they will not be visible. You cannot detect them using the finite dimensional distribution, and it will behave as a pure death process. Okay? So it depends on the whole evolution of this part. And maybe there are nice properties of the limit process. I did not focus on that.
Okay, thank you.
Thank you.
Any question in the room here?
Maybe I can add one comment that this is also an opportunity for me to thank Peter Jagev for me to come here at this institution for many years ago. And one of perhaps the thoughts of Peter was that I would complement his team where you worked with the supercritical situation, and I was focusing on the critical case. And yeah, so this is one of the results in this direction.
Okay. Any further questions? Okay, Serik. Thanks a lot for your talk.
Thank you for coming.
And as I mentioned, if anybody's interested in the recording, please write me. Thank you for participating.